Hi, welcome to this section where we are going to take a look at complex integrals. Right, now for the complex integrals, they will follow they are slightly similar to what we have already been doing. Okay, and when we are and to draw a line here and this. Okay, I want to draw two axes here, one for the complex integration and one for our normal integration, which we have been used to. Okay, so let us assume here for our normal integration we have y and we have x, and we have maybe an arbitrary curve here which is given by y is equals to f of x, and whenever we wanted to integrate, okay, maybe between the values of x equals to a and x equals to b, that is what we simply did. We represented it by the integral from a to b of our function here f of x with respect to x. So we integrated along this line, okay, along this line from x equals to a to x equals to b. That is the path we are following here. Okay, simply follow this path here. Now the story is slightly similar for our complex integration here, only that here this is like this is just like straight line. We are integrating along a straight line from x equals to a to x equals to b. However, remember we said that when we have complex numbers here, they are defined in a complex plane. Okay, here we have the real part of z, and then here we have the imaginary part of z. Alright, so since these ones are defined in the plane, it is important to note that we don't have just one single path which is going to represent the movement from the first complex number z1 to the other complex number. We have multiple paths which can lead us to multiple paths which we can take in moving from z1 to z2. Okay, they are multiple paths, it's not just one. They are numerous, and I will just do this just to illustrate. So maybe one could take this path, we can call this c1, or someone could have taken this path c2, or someone could have taken this path c3. Okay, so from z1 to z2 one can move along multiple paths when performing integration. However, this should give us the same results. Okay, it is this integration here should be independent of the path one takes. For our normal integration here for the functions here, real valued functions, we were simply moving along a straight interval. Okay, that is from x equals to a up to x equals to b. They are just the numbers on the number line, so it's just one particular direction we follow. Whereas here in the complex plane here, you can follow different paths. Okay, however, this path ideally should give us the same solution at the end. Alright, what else? So that means that when we are dealing with our complex integration here, okay, it is important for us to define the path which one is taking. Okay, so when we shall be integrating our complex numbers here, okay, have the imaginary part of z, which can be y, which we can call y, and then this is x, which is our real part of z. Okay, assuming we are moving from z1 So we are going to integrate from z1 to z2. Then we shall have to define the path which we are taking. If we call it maybe c, okay, one has to define this path c which we are going to take in the integration here. Since we can follow multiple paths, it will be important for us to define the particular path which we are going to take. All right. Okay, so what else do I need to, okay, so let us write down something here. So here, but we shall make some simplification as well. We can say that if we are integrating over this path, along this path c, okay, of our complex valued function f of z with respect to z, okay, we can write it, remember that we are going to say that f of z, we are going to write it as a function, okay, complex valued function, which has the real part and the imaginary part. So we can as well write this and then say we have u, okay, plus iv, okay. We all know that they are functions of x and y, so I'll just leave it at that. We are taking the integral over this path c, and then dz, okay, sorry, and then dz, yes, it's okay. Then dz, we are going to have it as dx plus I dy, not so? Yes, because we have our z equals to x plus iy, therefore changing z should be equals to dx plus I dy, and that is what we have here. So we can simplify this and then say we take the integral over this part c of u dx, okay, u dx, then what else, okay, how can we, which one do we come first, okay, then this and this, of course we know I squared is -1, so we shall have minus v dy, okay, then plus, then we can collect the ones which have i's alone, so we have the integral over c of v dx, okay, this v dx, and which other one has y, this is v dx, and okay, we have this and this give us that, then I should have this and this, okay, u plus, okay, I think the other one is integral over c, this u and this one here, u dy, and these are the ones which are the imaginary part here, okay. Yeah, you can get pen and paper and also try to look through and make sure that I haven't made any error here. So the way we can simplify is this way, and then later on we can also have a change of variables. We shall see this with examples. This will make our work easy. So we can have a change of variables where we shall write dx to be equal to dx dt times dt. Similarly, we shall say dy is equals to dy dt dt. Okay, so that now we can write and then say we have the integral of our part c f of z dz being equal to, so with the change of the change of variables, maybe now we have a new variable which is dt, so we can as well take, we shall change our limit c of integration, and then we just have this, okay, dt then minus alpha to beta v, then dy is dy dt dt, then plus I, the integral over c, then we have v, oh sorry, not over c, this is alpha to beta, and what do we have here, dx dt dt plus the integral alpha to beta u dy dt. Okay, so yeah, that is the procedure which we are going to adopt in here. Okay, so this is a brief. Okay, in summary, we say that for complex integration, okay, the difference with our normal integration of real valued function is that we can take multiple paths. Therefore, if we are going to integrate from one complex number z1 to the other, we shall have to also to define the integration path we are taking. So we can integrate over that path c over our function f of z, okay, which is made up of its real and imaginary parts, okay, and then we can break up the integral as we have done here, and then we can also have a change of variables, and then we can simplify it to this form here. Okay, now next we look at some important theorem which we are going to be using in these computations. Okay, so the theorem, let me start it on a new page here. The theorem that we are going to look at here is what we call Cauchy's, okay, this is h and y, Cauchy's theorem. So Cauchy's theorem is very important. It gives us a very, very important result. So here we have the imaginary part of z, and then we have the real part of z. Okay, so let us assume that now we have a closed path. A closed path. I want this to be smooth. I will let you know in a moment why I did that. In that direction, okay, it is counterclockwise. So usually they say that path which is in counterclockwise is positively oriented by convention. So we have our function f of z inside there. We have this path which we are going to call c, and we have said that this is a closed path. Okay, it is a what? Closed path. So Cauchy's theorem here tells us that suppose f of z is a complex function. Suppose f of z is a complex function and c is a closed curve, and c is a closed curve in the complex plane, and this is a closed curve in the complex plane. Okay, if f of z is analytic, okay, some people go ahead and say that if it is holomorphic, in math here, every word you use here has quite implications. So the idea here is we are going to really use the Cauchy's theorem. Okay, we are not going to go into details in the technicalities. That's why is this supposed to be analytic, or what's the difference if someone says holomorphic, or if someone insists that it has to be analytic. We are not going to go into those details. Okay, so in here the spirit of this is not the mathematical the rigorous mathematics and stuff like that. It is for us to understand how this can be used. Okay, if you really want to go so much into the rigorous math and what, perhaps you could take up a real math course in this complex analysis. So anyone who's an expert in this, please, if you look at the video here and then you say, this video has so many technical glitches here and there in misuse of the words and what, I apologize in advance. Okay, so f of z is analytic. Okay, some people say holomorphic. on, okay, it is analytic. I'll go with analytic, on and everywhere, on and everywhere inside, on and everywhere inside C. Okay, further we have that C on and everywhere inside that. Further we say that C is a simple curve. So what do we mean by simple? By simple here, okay, by simple we mean that this is smooth. Okay, in other words, we are not going to accept, you know, sharp corners or bends. You know that in sharp corners in mathematics, these are really troublesome. For instance, you know that at a sharp corner you cannot, you know, add the derivative of a function is not defined at such a point. Why? Because you cannot draw a unique tangent to that point. You know, you can have infinitely many tangents, you know, at that point. Okay, so that is why okay, now it doesn't make sense. let me draw it well. I was just reminding you why sharp corners are kind of problematic here in math. For instance, they say that if you have that sharp corner there, okay, maybe to be precise, let us say the absolute value function, okay, if this is y and this is x, then we say we cannot have, you know, it cannot be differentiable at that point. And why? For a simple reason that you can have infinitely many tangents which you can draw at that point. That is a tangent, that is a tangent, that is another tangent, you know, that is another tangent. So since you have many tangents, okay, can that T1, T3, T4, so it is not differentiable, like it's not unique. You cannot have a unique, you know, value for the derivative at that point. So that is one of the reasons. Okay, so those, you know, domains, okay, which are sharp or which are not continuous, okay, the next thing we are going to say that it is smooth, it has to be continuous. Okay, continuous, in other words, we have no jump, no gap. Also in math, you know that all those functions there in your calculus, I hope you remember, we had some problems, those functions which skip a value, which have a jump, okay, and so on. So that's what we are talking about. We don't, I mean, if it is continuous, then there is no jump, there is no gap, it is just, you know, smooth throughout without, you know, any gap in it. And what else? Another important property here when we are talking about this simple is that it is non-intersecting. Non-intersecting. Intersecting. So if it is intersecting, maybe you could have something like this. It intersects itself and then comes like that. That is not simple. Okay? This is not simple. Why? It intersects itself at a certain point. So, but don't worry, everything that we are going to be dealing with in this course is going to be following, you know, that it is just simple. We are dealing with this, okay? I'm not going to try to be catching you or testing you that is it simple, is it not simple, and stuff like that. So once again, if it is analytic, on and everywhere in C, inside C, okay, don't forget this, here on and everywhere inside C, and we have that C is a simple curve, simple in the sense that it is smooth, it is continuous, and it is non-intersecting, okay, then something very important here, then we have that this contour integral, okay, the contour integral of a c, that is the closed path integral of f of c with respect to z equals to 0. Wow. So much work just to write that the integral of over the closed path of that function f of z with respect to z is simply 0. So now, yes, it is important. We shall see later on in a few examples. Okay, so once more, you have, our domain here. You have a function which is defined or which is analytic. Of course, if it is analytic, one simple way we shall just see is that it has to be defined at, all values. If there is any value inside C where it is not defined, where the function is not defined, then we shall say the function is not analytic at that particular point. For example, if you have our function, let us say f of z equals to 1 over z, we know that it is not defined at the point z equals to 0. So at that point z is equals to 0, we shall say it is not analytic. It is not defined at z equals to 0, i.e. it is not analytic. Okay? Stuff like that. It is not defined at that point. So what else here? Yes, our function f of z is analytic inside the closed path C, a path which is simple, okay? And what else? It's simple in the sense that it is smooth, continuous, and non-intersecting. Then the contour integral, that is the integral over this closed path C, okay, of f of z is equal to 0. That is Cauchy's theorem. Okay? Yes, so once more, it is analytic as long as it has no singularity. So I have brought up a new term here, which we shall make mention of also, singularity. Singularity simply means the same thing I've talked about here, the value like z0 for the function f of z, sorry, this is f of z, not f of x. For the function f of z is equals to 1 over z, it has a singular point at z equals to 0. Okay? Great. So if you look some other text, they may add things like maybe this, this path has to be positively oriented, it has no finite number of corners. Anyway, I just try to make it as simple as possible without necessarily changing the definition. I hope it makes some sense here. So, similar to Cauchy's theorem here, I don't want to leave it hanging. I could have stopped the video here, but we need to look at something important and also finish with an example here. Similar to that is what we call Cauchy's integral theorem. Now this is Cauchy's, the other one is Cauchy's theorem, but now this is Cauchy's integral formula, actually not theorem, formula. Okay? Now what does Cauchy's integral formula tell us? It tells us that if f of z is analytic, again, some people will write holomorphic. If it is analytic, okay, on and inside a simple closed curve C, okay, then we are going to say that then f of z naught, okay, can be given as 1 over 2 pi I times the contour integral, okay, f of z over z minus z naught dz. Okay, and one important thing to note, I'll put it even here in red, is that z naught is inside C. Z0 has to be inside C. Okay, now I'll just give you an intuitive interpretation of this Cauchy's integral formula. So Cauchy's integral formula simply tells us that if we have any function that possesses a singularity at the point Z0, we have any function that possesses a singularity at Z0. Okay, we have any function f which possesses a singularity at the point z equals to Z0, then we can evaluate, okay, we can evaluate this integral here. Then we can evaluate this integral. We can evaluate this integral. We can evaluate this integral. Okay, by evaluating the value of the function at that point. By evaluating the value of the function at that point. Okay, and multiplying it with this factor here, 2 pi I. I hope you realize that what we have done here is simply we have made this the subject here. We can evaluate this integral here by simply getting f of Z0 and then multiplying it by 2 pi I. In other words, just take this here and then we bring this here. That's it. Makes life very, very easy. So that means that we can be given expressions as long as we can, you know, express them in this form here, and we check that these conditions here are met, that it is analytic or holomorphic on and inside the closed path C, okay, and that our singularity is inside C. Then we can evaluate the value of this integral here by simply getting the value of the function at that singular point and multiplying it by 2 pi I. Okay, so I think we can see here we have said that if the function is analytic on inside R, but it must have a singularity Z0 inside C, at least one point which is singular. Otherwise, if it does not have at least one singular point, just like here under Cauchy's theorem, remember Cauchy's theorem says that f of z is a function, blah 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 blah, it is analytic, okay, on and everywhere inside C. Everywhere meaning there is no single point where it has a singularity. Then the value of that integral here is 0. So for us here, if it actually had any singularity, if it did not have any point anywhere inside C where it is singular, then the value of this integral here will simply be 0. But since we know at least there is a point Z0 inside C which is singular, okay, then that means that this integral here is not going to be 0. However, if it was, then we simply use Cauchy's theorem. So here, the important thing to note is that our singular point here has to be inside C. Okay? Okay, let us conclude this with an example, and then in the next video we shall look at even many more examples. So, let us look at an example here. Okay? So, the example here is that we want to integrate, okay, the integral over the path C, which is given by the modulus of z equals to 2, and then what do we have here of this expression, z over z minus 1 dz. So perhaps we could just do a simple sketch. By the way, I hope you remember, I told you that at the start of this course, the idea is that we remember the basics. I hope you know that this is simply that. So when we have this equals to 2, we simply mean that x squared plus y squared is equals to 2, and I hope you know that this is simply a circle, okay, centered at the origin and having radius 2. So So we have that, and then we have our circle. Can I draw a shape? Okay, I don't have time for that. Let me just draw that. So we have our circle. Okay, this is 2 because our radius is 2, and you know, so that is 2. It is centered at the origin, and yes, what else? That's it. Okay, that's it. So we want to evaluate this here. Okay, so one, we make use of our whatever. We know that for this, okay, we know that we have a singular point in here. Okay, let me go back here. So we have this one here. If it is written in this expression here, z minus z naught, z minus z naught, and the minus z naught is our singular point. Okay, so here you realize that we have written that in that form, z minus z naught. In other words, we have that our z naught is equal to 1, and indeed we know that at z equals to 1, okay, we have a singularity here, because z over 1 minus 1 is, you know, z over 0. It is not defined at that point. We have the singular point, and that singular point z naught is inside our paths, which is represented by the circle and given by that equation that the modulus of z equals to 2. The z naught equals to 1 is inside that circle of radius 2. Okay, so if f of z is analytic, okay, on and inside a simple closed path C, so apart from that point z equals to 1, we can see that our function here, z over z minus 1, is analytic. It is defined at all points on C, that is on the boundary here when z is 2, or any other point inside. It is well defined. Okay, z over z minus 1 is well defined, except at that point z naught is equals to 1, so that is our singular point there. So it is analytic on and inside R. Then we have this expression, so we are going to make use of this expression, and we see how we can compute this integral here. So we are going to say that this integral here over the path defined by the modulus of z is equals to 2 of z over z minus 1 dz, okay, is simply going to be now 2 pi I, okay, this one here. Remember this, in the form we have this as z, and then here in the denominator we have z minus 1. Not so? So we simply have that this integral of z over z minus 1 is simply going to be equal, given by f evaluated at z naught times 2 pi I. So we are going to say it is 2 pi I times f evaluated at z naught. So which is going to be 2 pi I f evaluated at, what is z naught? We know that z naught is 1. So which is going to be 2 pi I. Maybe one thing I forgot here is to say f of z. Remember, you just look at the formula here. Remember, we have f of z over z minus z naught. So what we actually have here is that f of z all over z minus z naught. That is why you say z naught is 1, and then f of z is simply the numerator here, which is z. So if f of z is z, that means that f of 1 is simply going to be 1. Okay, f of z naught is going to, in other words, f of z is z. That means that f of z naught is equals to z naught. And what is z naught? That is f of 1 is equals to 1, the value itself. So that means that the integral here, the closed path integral, okay, over this path, okay, is simply equal to 2 pi I. That's it. Okay, yeah, so that is just the introduction. In the next we shall look at numerous examples just to try to drive that point home. So I hope you enjoy it, and see you in the next video.